Before we started looking at refraction, we found that a concave mirror could form an image by taking light and converging that light. In particular, if we looked at incoming parallel rays, what the concave mirror did was to reflect that light back to a single point, and that's what allowed the concave mirror to form an image, essentially. Well, let's see if we can figure out some way to do that with refraction. Last time, one of the things we looked at was a prism. So let's see how a prism will refract light. So let's draw this prism here like this. And let's take a look at what this does to light. Now, we'll take a look at too much. Okay, here's our laser. And what I'll do is take a look at what an incoming ray that is parallel to the base of the prism. What does that do? Well, we put that here, and what we find is that it is refracted twice, at the front and at the back, and comes out in a line down that way. And it doesn't matter if I move this down, it still comes out in essentially the same direction. So let's draw those in here. Let's take this off. Let's draw those rays in. So we've got one ray coming in here. Now, what's going to happen? Well, we're in air, we're going into a medium with a higher index of refraction. We know when a ray goes from a lower index to a higher index, it gets refracted toward the perpendicular. So if we draw in the perpendicular here, we know that ray is going to be bent toward the perpendicular, which means it's going to be bent downward. So it's going to be refracted downward like that. Now, as it leaves the medium, leaves the plexiglass, say, and enters air, we know that it's going to be bent away from the perpendicular. So we'll draw in another perpendicular over here. And now it's going to be bent away, which again is going to be downward. So the ray is going to be bent again downward, something like that. And that's just what we saw when we actually had the prism up there. A parallel ray will strike the prism at the same angle as the first one, so it will be refracted at the same angle. That will then strike the backside at the same angle as this one, and will come out again parallel. And another ray coming in here will come out parallel there. So we have these three incoming rays all refracted as parallel rays over there. Well, now let's add another prism. Let's add a second prism, but in this case, let's add a prism that is upside down, or just reversed from the top one, like this, with the same parallel side as the one above it. So let's imagine we have a situation then like this. So we've got the same prism underneath now. Well, what's going to happen to three more rays, say, that we draw in here? Well, rather than being refracted downward, these will all be refracted upward and parallel. So we end up with something that looks like that, essentially. Well, we're getting there. These two prisms are refracting rays. They're not bringing them to a single point, but they are making them converge to some extent. Basically, rays near the central axis are being refracted close to the prisms. Rays at the top and the bottom are being refracted farther, or far from the prisms. Ones in the middle being refracted somewhere in the middle. If we could somehow bring those points together, we would have an object that would refract all of these incoming rays, parallel rays, to the same point. Well, to get this a little bit further out, we need to maybe make the curvature or make the angle here not quite as steep. So let's imagine that maybe we could smooth this section out a little bit and make it not quite so bent. To pull this one in, we need to bend the top and the bottom a little bit more. So let's imagine that maybe we bend the top and the bottom a little bit more. Well, what do we end up with? We end up with a lens. In this case, we end up with something nicely curved, lens-shaped, you might say, and we could arrange this front and back surface so that these incoming parallel rays all get refracted to a single point, something like that. There we go. So, we've just done exactly what we wanted to do. We arranged some kind of refracting situation that brings all of these incoming parallel rays and brings them all to the same point of convergence. This is what we will call the focal point of the lens. Okay, very, very good. Now, one of the important ideas that we saw last time, or previously, is that if we have some, say, refraction, where a ray will go from, say, some point A to point B, we know this will occur according to our law of refraction, then if we were to actually have the ray to go from point B and we send it back in the other way, it's going to refract and come back to point A. So any ray that can go from A to B could also go from B to A. Well, we can imagine this situation here if we were to take our rays and exactly reverse them. Imagine we had incoming parallel rays from the right traveling to the left. Well, if our lens was symmetric, we would expect this then to all be refracted to another point on the left side of the lens, and so we would expect to have another focal point. So our lens actually has two focal points, one on the right, one on the left. And if the lens is symmetric, we would certainly expect the distance from the lens to the focal point on the right should be the same. I didn't quite draw it that way, but it should be the same as the distance from the lens to the focal point on the left. The fact of the matter is that if the lens is thin and we don't have to worry about kind of the effect of the ray actually inside the lens, we don't even have to have the lens being perfectly symmetric on both sides. We could have differences on the two sides, and essentially the focal points will be the same distance from the lens. So we'll just assume that they are. The distance from the lens to the focal point, this is what we'll call the focal length. And we'll identify that with the letter F, just like we did with mirrors. Okay, very, very good. There's one more ray I want to mention here, and that is what happens to a ray that passes through the center of the mirror. So imagine, and I mean the lens, the very central point of the lens. A ray that comes in here will be refracted at this surface, refracted at this surface. These two surfaces will essentially be parallel to each other, approximately parallel, and essentially the ray is going to come right back out in the same direction. So we will make the approximation that any ray that passes through the center of the lens will come straight through and go on a straight, undeviated path. Now, to make sure that all of these things work just the way we say, we need to make a little approximation that this is going to be, as I mentioned before, whoops. A thin lens. In other words, the thickness of the lens in the thickest part has to be small compared to the overall size of the lens, say, lengthwise. That essentially then gives us the properties that we've just been talking about. Two equidistant focal points and a ray passing through the center that goes through undeviated. Okay, so given these rays, we are going to do something just like we did before. We're going to do a ray tracing diagram. For a lens, we're going to draw a thin lens, again with a straight line, just like we did a straight line for the mirrors. Even though we know the mirrors are curved, concave or convex, we're going to draw the lens as a straight line, kind of approximating this idea of a thin lens. But to indicate this overall shape of the lens, we'll put a little arrowhead at the top and the bottom. So this is kind of to symbolize the overall shape of the lens. So when we have these two symbols at the top and the bottom, we'll know that we've got a lens that converges incoming parallel rays, and so this is what we will refer to as a converging lens. A converging lens takes incoming parallel rays and converges them, in other words, brings them together to a single point. All right. Let's see if we can draw a ray tracing diagram for the lens just like we did for the mirror. First thing, let's draw in our principal axis. So, with a ruler or some straight edge, we're going to draw a nice horizontal straight line. As horizontal and straight as we can make it. Here we go. Now, we'll draw in our lens perpendicular to the principal axis. Draw in your lens. Put our tabs on it, top and bottom, to indicate that this is a converging lens. Now, let's choose a focal point. So we're going to choose two focal points, equidistant on both sides. Now try and do this carefully. Draw in a focal point on each side, both the same distance from the lens. Now we're going to put in an object. Let's just, for the sake of consistency with all of our drawings, let's put the object exactly twice as far from the mirror as the focal length. So right over here, we'll draw in our object. There we go. So we've got our converging lens, two focal points. Our object is then at a distance that is exactly twice the focal length from the lens. Now, let's draw in our three principal rays. Just like we did for the mirror, we'll have three principal rays in our ray tracing diagram. What's the first ray? The first ray, we know, is if a ray comes in parallel to the principal axis, we know that an incoming parallel ray is converged through the distant focal point. So an incoming parallel ray will get refracted through the focal point like that. Now, let's indicate the direction of these two rays like that. We also know that a ray that comes from this focal point will come out parallel. Now, remember the other way, we said a ray that came in parallel this way would be refracted through the focal point. Another way of saying that is that a ray that comes from this focal point will be refracted out parallel. Well, let's draw a ray that comes from this focal point. Well, we need to draw the light as coming from our object, so we'll go from the object through the focal point. So that ray we know is coming from the focal point. This must come out parallel. So draw that ray then coming out parallel. There we go. Our third ray is the one that goes through the center of the lens. So we'll draw one more ray through the center of the lens, and if we draw this carefully, and I tried to do it as carefully as possible, then what we find is that that central ray goes right through the same point. And just like with the mirror drawings, we then have that the image is, the tip of the image is right here where all the rays converge. the tail of the image is on the principal axis, and there we go. There is our image. And here is our object. There we go. So let's write down what our three principal rays are. Okay, ray number one. We'll kind of write this shorthand. So a ray that comes in parallel goes out through the focal point. So in parallel, meaning in parallel to the principal axis, is refracted out through the focal point. Second ray, in through focal point, and in this case we mean the focal point on the side with the object, so in through the focal point, out parallel. And then finally the one through the center, in through the center, straight through. There we go. So there are our three principal rays and an example for an object, in this case an object that was at a distance of twice the focal length. Now it turns out we can analyze this in the same way that we did with the mirrors, using a relationship that will describe these distances and the focal length of the lens. If we define, as I did before, the distance from the focal point to the lens, f, our focal length, the distance from the object to the lens, this is dO, our object distance, the distance from the lens to the image, this is di, our image distance, then we find that the relationship between the object distance, the image distance, and the focal length follows what we will call the lens equation. Now don't confuse this with the mirror equation. It's completely different. This is the lens equation. The lens equation is 1 over dO plus 1 over di equals 1 over f. And that is the lens equation. Not to be confused with the mirror equation. Now, let's stick some numbers in here and just see how that works. Well, let's say, let's pick maybe 10 centimeters for our focal length. Then our object distance would be, say, 20 centimeters. The image distance, well, let's figure that out. So we have 1 over dO plus 1 over di equals 1 over f. So 1 over di equals 1 over f minus 1 over dO. With a focal length of 10 centimeters, we'll have 1 over 10 centimeters minus dO, that'll be 1 over 20 centimeters. So we have 1 over 10, which is 2 over 20. 2 over 20 minus 1 over 20 is 1 over 20. So that is 1 over 20 centimeters. di equals 20 centimeters. And that's exactly what we find. We seem to find an image distance which is exactly the same as the object distance, the image just being on the back side of the lens. So notice one important difference here. The image in this case is on the other side of the lens as opposed to the front side of the mirror, which is what we found for a concave mirror. The light goes through lenses as opposed to being reflected by mirrors. We also have the same definition for magnification. The magnification will be minus di over dO, which in this case is going to be negative 20 centimeters, over dO, which is 20 centimeters, which gives us a value of negative 1. And again, we have the same convention that we did for mirrors. The negative sign tells us what? it tells us that the image is inverted, which is exactly what we see, and a magnitude of 1, which tells us the size of the image is the same size as the object, and that is pretty much what we see there. So, very, very good. Lens equation, definition for magnification, they apply to lenses very, very much the same way that our equations have applied to mirrors. All right, let's try another one. Let's do another converging lens diagram, except this time let's put the object inside the focal length, and let's see what happens. Again, let's draw our principal axis. Draw in our lens. Let's draw in our focal points. And an object. And in this case, let's put our object, let's say, half of the focal length. So we'll actually put it inside the focal length. Now what happens? Well, we're going to draw our same three principal axes, principal rays, sorry. First one, in parallel, out through the focal point. So I really suggest that you do this with a ruler or a straight edge or something like that to make these as accurate as possible. And if you can do it on graph paper, it's even better, because then you can make sure that parallel rays are really parallel. So come in here with an incoming parallel ray, indicate the direction. This goes through the focal point, so this gets refracted down through the focal point. There we go. Then, in through the focal point, out parallel. So we need a ray that goes from the object through the focal point. Now if I do it this way, that's not going to hit the lens, so that's not going to work. What I need to do is have a ray coming from the object, but from the direction of the focal point. So I'm going to draw the ray going up this way, from the object, coming from the direction of the focal point. So we need to modify this a little bit, just conceptually. Rather than going in through the focal point, we're going to have it go in at least from the direction of the focal point. So here's our second ray coming in that way. Now what does it do? In through the focal point, in from the focal point, out parallel. So our next ray then comes out parallel. There we go. Here's our second ray. Third ray, in through the center, straight through. So we can draw our third ray in through the center, straight through. There we go. And there's our third ray. Well, we look over here, these rays do not converge. They don't come together at any place over here. However, we'll notice if we could trace them back, they appear to come from some point over here. In other words, if you were looking at these rays, if you'll remember talking about this before, you're looking at these rays, your eye will trace those rays back to the point where they appear to come from. So we'll trace these rays back. Where do they seem to come from? Well, trace this one back, trace this one back, trace this one back, and they seem to come from a consistent point back over here. In other words, our image will look like this. There. So there's our image. Here's our object, and here's the image. There we go. Now, what do we notice about it in this case? Well, the rays do not come together, So what kind of image do we have? It's a virtual image. I didn't mention it before, but what kind of image was the first drawing? That would have been a real image. The rays did cross, the rays physically crossed, and so that was a real image. In this case, the rays appear to come from the image, and so this is a virtual image. It is upright, and it does seem to be magnified, we might say maybe twice the original size. Well, let's stick the numbers in our lens equation and see what we get.